Hello and welcome to the last of the lectures in this week 7 of this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. During this week of lectures, we have concentrated on similarity-based reasoning. We have seen there are two major types of similarity-based reasoning, that of the fuzzy inference system proposed by Mamdani and Asilian, which is typically called the Mamdani fuzzy system. We have seen how to build a Mamdani fuzzy inference system using the fuzzy logic toolbox in Matlab. We have approximated some specific given mathematical functions, and we have also seen how you could build a Mamdani fuzzy inference system in a given practical application. In this lecture, we will look at the second of the major similarity-based reasoning inference schemes, that of the Takagi-Sugeno-Kang fuzzy system. We'll once again build a simple TSK fuzzy inference system using Matlab, the fuzzy logic toolbox in Matlab. We will also visit the defuzzification process briefly, and finally we will give a pictorial depiction of both the fuzzy relational inference mechanisms and the similarity-based reasoning schemes. Perhaps you could then easily see some of the similarities that exist. Let's revisit the mechanism underlying the similarity-based reasoning scheme. So we are given a single input, single output rule base of this form. If x tilde as ai, then y tilde as bi. In the first step, given an a dash, which is a fuzzy set on x, we match this a dash, the given input, to each of the antecedents ai using a matching function and obtain the similarity value si, which is typically in the interval 0-1, the range of 0-1. In the second step, we use the similarity value to modify the consequence of each of the rules. So given si and bi, we modify the consequent to a bi dash, which is again a fuzzy set on y. Now, we obtain such modified consequence bi dash for each of these i's, and the third step, we aggregate all of them to a single b dash. In the final step, if required, we defuzzify it. That means map this b dash, which is a fuzzy set on y, to some value in the domain of the set y. There is also a pre-processing step, that is, often we may be given an input which is a real value, not a fuzzy set. Then in that case, we apply the fuzzification operation to obtain the a dash, the input to be given to the system. We have seen these 5 steps in depth. Note that when we need to specify a similarity-based reasoning scheme, these are the parameters we need to specify. Px and py are the fuzzy coverings on x and y. R of ai bj are the rules. Ai's are the antecedents which come from px. Bj's are the consequents which are picked from py. And these are associated to form the rule base. H is the fuzzifier. M is the matching function. J is the modification function. G is the aggregation function. And small g is the defuzzifier. Also recall, when we discussed the different classifications that you could have on fuzzy if-then rules, one type of classification we came up with was based on the nature of the consequent. We have seen that typically fuzzy if-then rules have fuzzy sets on both antecedent and consequents. However, we could also have just a function on x, a real valued function on x, or y, real valued function on x as the y. So in that case, the rule would read like this: if x tilde is a, then y is equal to f of x. So essentially this y is obtained directly from the given input x. So this is a function of x, y is given as a function of x, typically a real valued function of x. And we have seen that the same can happen in the case of a multi-input single output rule. So the y is dependent on x1 to xm, the m-dimensional input vector. Now let's look at the Takagi-Sugeno-Kang fuzzy inference system. Let's compare it with the known Mamdani inference scheme. The first difference between a TSK and Mamdani fuzzy inference system, note that both of them are similarity based reasoning schemes. So the first difference is in the consequence of the rule. While in the case of Mamdani, fuzzy sets form the consequence. In the case of Takagi-Sugeno-Kang fuzzy systems, what we have are actually functions of x as the consequence. So you would have rules of the form: if x tilde is a1, then y is equal to f1 of x. If x tilde is an, then y is equal to fn of x, so on and so forth. Now, these functions f1, f2, so on till fn, they are real valued functions. They could be polynomials, they could be linear functions, they could be non-linear functions. There are no restrictions on the class of functions to which FIs can belong. This is the first difference. Secondly, if you look at the overall inference scheme itself as functions, then in the case of Mamdani, typically we input a fuzzy set on x and we obtain a fuzzy set on y. Of course, you could always defuzzify and get an output over the domain y. But typically, Mamdani fuzzy systems are looked at like this. So in that sense, they are mapping from f of x to f of y. However, TSK fuzzy systems typically are considered as mappings from x to y. Of course, we will suitably fuzzify it to process it, but you could look at them as just functions from x to y. Let's look at the inference itself. There lies another difference here. So this is the rule base that we are considering. Note that the output or the consequent functions y are functions of x. So now, given an x dash in x, the weighted sum TSK is given like this. The output y dash is obtained like this: sigma over si dot fi of x dash. Essentially, it is a weighted sum weighted by si, and fi of x dash is the value that fi takes at the given input x dash. Note that we are actually giving just a value x dash from x. In the case of weighted average TSK, all we are going to do is use these similarity values as weights and do a weighted average of these weights with respect to the function values at x dash taken by the consequence of all the rules. So essentially, it's either a weighted sum of the similarity values into the function values at x dash, or the weighted average of the similarity values into the function values at x dash. So note that SIs are the similarity values. So typically you could use the MZ function, in which case we know that the similarity SI is nothing but the membership value of x dash at AI. Of course, you could use any one of those family of matching functions where you suitably change these two operations, plus and cross. Note that AX dash here symbolizes the singleton fuzzified x dash. That means that x is equal to x dash, you are fuzzifying it in a singleton way. It takes the corresponding fuzzy set takes the value 1 at x is equal to x dash and 0 everywhere else. And if you are using such a matching function where SA is in fact AI of x dash, if Px, the fuzzy covering on x, if it does form a Rospini partition, and if each one of the fuzzy sets features in the antecedent of the rule, so essentially we have a complete rule base, then what is easy to see is that the output from both the weighted sum TSK and the weighted average TSK, they are going to be equal. Because in that case, what we would have is sigma JSJ is actually going to turn out to be 1 because of Rospini partition. There's essentially AJ of x dash. So they will turn out to be 1, in which case these two are in fact identical. So TSK inference is pretty simple. It is classified under SBR because given an input, we are finding the similarity to each of the consequence. We are modifying the similarity to the antecedents. We are modifying the consequence using these similarity values and aggregating them. But can we really see it as an SBR? Well, in some sense, yes. look at it. These are the formulae that we have. These are MZ and JMVR, essentially this is a Z-ace matching function, and this could be looked at as just the product of the similarity value into the consequent fuzzy setting rule. So essentially it's a product operation. You could look at it as a product T. Now how do Mamdani and TSK compare as SBRs? Let's concentrate on the TSK weighted sum. Of course, we could also in some convoluted way look at weighted average TSK also as an SBR in the matching it or mapping it to the different operations that we have given of H, M, J, G and G. But for the moment, let's concentrate only on the weighted sum TSK fuzzy system. So we know that the matching function that you could use is typically the Z-ace matching function. Of course, you could use any one of the major class of matching functions wherein you change those two operations plus and times cross. The modification function in the case of Mamdani fuzzy system is essentially this. You could also just look at it as product, but in the case since we are dealing with only real numbers here, we could just look at it as product here as the corresponding modification function. For the aggregation, all we are doing is using the summation, and since in a Mamdani fuzzy inference system you get an output which is a fuzzy set on Y, we need a defuzzification, whereas here you could just look at this as itself a real value. So that means we are falling into the domain of Y. Even though Matlab looks at this entire operation as a defuzzification operation, we could look at this as modification followed by aggregation. So this in a nutshell is TSK inference system. This is how we infer, and this is how we could map it to the different stages or steps in a similarity-based reasoning scheme. And we see some correlations or relationships the way Mamdani and TSK fuzzy systems either differ or also compare favorably with respect to each other. Now, we'll take a look at how to build a particular TSK fuzzy inference system using the fuzzy logic toolbox in Matlab. Note that these are the two things that we'll be looking at, and with respect to the TSK weighted sum fuzzy inference system, this is how the different steps correspond to. Use MZ as the matching function or one of those matching functions in those classes, those class of operations where you only change the plus and the times. Modification is product typically, and aggregation is the summation. Let's look at a particular Matlab implementation. And fuzzy logic toolbox allows you to implement the function on the consequent side either using a constant function or a linear function. That means either you can have just AI where VA is 0 or it is AA plus BIX for each of those consequents in the end rules that you have. Let's look at implementing a TSK FIS in Matlab. Well, what we will do is build a TSK fuzzy inference system to actually capture the behavior of histogram equalization as we saw in the previous lecture. So once again, this is the image we are going to consider. Clearly, our goal is to enhance the contrast in this image. If you look at the corresponding histogram of pixel intensities, we have seen the dynamic range of this is limited. It is not the entire 0 to 55 interval, and this is what we want to extend or expand. We have seen that the dynamic range is actually given by this interval 97 to 43. So that means the pixel intensities lie between these values. If you apply the histogram equalization, we have seen in the previous lecture, this is the kind of contrast enhancement that you will obtain. And in essence, histogram equalization can be seen as making such a monotonic transformation to this histogram, and that's how it is expanding the dynamic range of the pixel intensities. We want to implement or capture this monotonic behavior using a fuzzy inference system. Remember, it is the monotonic behavior of this expansion of this dynamic range that we want to capture. Histogram equalization is one mechanical way of doing it. Now we would like to implement a TSK Fuzzy Inference System to come up with a function which shows similar behavior that when applied on this image will allow us to obtain a contrast enhanced image. So once again, that means we need to actually find the fuzzy coverings on X and Y. It is clear X is the dynamic range, which is essentially 97 to 243, and Y is the entire interval into which we want to extend or stretch this dynamic range into, which is the 0 to 55 interval. Let us once again split the dynamic range, the actual dynamic range of the image into 20 equal intervals and fix triangular membership functions on them. So that means we are going to have 21 such membership functions. This will form the fuzzy covering of the input space. Each one of them will also act as an antecedent. Now the question is, to whom should we relate this to? For the moment, let's only consider a TSK Fuzzy Inference System where the consequent function is a constant function. So essentially, we are only going to pick these points to be mapped into. These are 21 equispaced points. So that means you have 20 equal width intervals between 0 and 255. Let's look at how the TSK Fuzzy Inference System itself would look like. As was mentioned, you see here, this is a matching function from the family of matching functions to which Zardes and the Smith-Magre matching functions belong. What we called as modification is implication here and aggregation is here. You can see that Matlab calls weighted average or weighted sum as the defuzzification, which of course is a defuzzifying operation. But instead of this defuzzification operation, we can also look at the TSK Fuzzy system being implemented as using the product for the modification or implication and the sum for the aggregation. Well, now let's look at how the rules are. This is essentially what we had yesterday or the previous lecture. So these are the input membership functions, the way we have done it in when we're trying to capture the behavior of histogram equalization through Mamdani fuzzy inference system. Now you will see that in the case of output membership functions, while it is not shown here, you will see that it is in fact, so the ninth membership function is mapped to a constant. So f9 of x is the constant function 102, that's what we want, and f10 is the constant function 114.8, and f11 is the constant function 127.5. So this is what we have here. Let's look at the rules themselves. It's easy to see now that these are the input fuzzy sets which become antecedents. These are the output constant functions which are the consequence. Now, just as it happened in the previous case, the dynamic range starts from 97. So if the input is 97, the output is 0. If it is 100, it starts to increase, it goes to 5.2. If it is 120, it goes to 40, 190, it goes to 162. If it is 240, it is almost 249, it is beginning to saturate. At 245, it is 254. So you see that we are actually getting a monotonic transformation of this dynamic range into the entire interval 0 to 55. Let's look at the surface. So this is essentially the input-output mapping that we had from the Mamdani fuzzy inference system that we built. Of course, the inputs are same. The outputs, we have taken it to be just the centers of the output membership function that we had for the Mamdani fuzzy inference case. So that both of these are matching is not really surprising. So this is what we have as the output function. This is the mapping that this fuzzy inference system actually captures. Now let's look at applying this fuzzy inference system, TSK Fuzzy Inference System, to these images. So this is the original image we had. This is the histogram equalized image and this is the fuzzy inference system applied image. So when we gave this input image to the TSK Fuzzy Inference System, this is the contrast enhanced image that we obtained. Let us take a brief detour to look at the defuzzification mechanism itself. For that, let's consider a simple Mamdani fuzzy inference system. In this, we are actually trying to approximate the identity function. But clearly, this function, the rule base that we have constructed, is not going to approximate it, but that's not the point here. We want to see the effect of different defuzzification procedures or mechanisms, operations on the output. Now, if we want to approximate the identity function, then what we want is, when we give the input to be 0.5, we are expecting 0.5 to be the output. However, we see here, this is the overall output fuzzy set, B dash, and this is the corresponding defuzzification operation that we have used. SOM stands for smallest of maxima. So we see here, in this fuzzy set, the kernel belongs to this part, and the smallest of maxima means the first of the points to which the kernel belongs. So we take the kernel, which is part of the support, over which the fuzzy set assumes the value 1, or it could also be that part of the support where it attains its maximum value, the height, the support of the height. So SOM stands for smallest of maxima, which means essentially you are considering that interval over which attains its maximum value and taking the infimum of those points, which in this case is 0.38. Instead of, note that for 0.5 we are in fact expecting 0.5 here, but that's not what we are getting. We are getting 0.38. What if we instead take mean of maximum? You see here, it has moved from the infimum of the corresponding support to the middle point over which it takes the maximum membership values. In this case, it does look like it is 1. And you see, already the output has moved to 0.445. So from earlier, it was 0.38 for the given input of 0.5. Now it has moved to 0.45. What if we take the centroid defuzzification? Now it has moved back a bit, so it is 0.432. If you use the bisector defuzzification operation, it is 0.43. But there is one more left, LOM, which stands for largest of maximum. When we use that, we see that it's almost there. So for 0.5, we are getting 0.5, and in fact for 0.51, we would get 0.5. So you see here, by adjusting the defuzzification operation appropriately, we can at times achieve the desired result. Let's stay with this for the moment. Let's look at the surface that we have got here. Note that we actually want to approximate the identity function. However, this is the mapping that we are obtaining. If you use smallest of maxima, you see here, this function is not only not approximating the identity function, but is quite wiggly. And it is also not monotonic, even though identity function is monotonic on the unit interval. If you use the last of maxima, well, at around 0.5, it is doing a good job. It is in fact hitting the diagonal of this function, the identity function. But in other cases, you see that it is not actually doing the job. That means it is not the identity function. However, it seems to be monotonic. That means once it goes up, it does not come down. If you apply the mean of maxima, you see that not only is it not approximating it well, but it also loses its monotonicity property. And while these are continuous, you see the sharp edges, and so you know that these are not differentiable. Instead, if you apply the centroid defuzzification scheme, At least in some parts of the domain, it seems more or less smooth. So this should clearly demonstrate to you that by appropriately changing the defuzzification operation, we can in fact expect to change the output function to a certain extent. And typically when we want to tweak a function, because we are going from some heuristics in building these fuzzy inference systems, so we have lots of degrees of freedom in the form of defuzzifier h, fuzzifier h, matching function m, modification function j, aggregation function g, and the defuzzifier function g. So all of these degrees of freedom can be put to good use to actually come up with a function that we believe approximates the system function quite well. Well, in the last 2 weeks of lectures, we have looked at fuzzy relational inference and the similarity based reasoning. Let us revisit them in a very pictorial way. So please recall that in the case of fuzzy relational inference, you had two inference strategies: first aggregate then infer, or first infer then aggregate. Now what we have to infer is, given an input a dash, which is a fuzzy set on x, we want the output to be a fuzzy set on y, which we have indicated as b dash. To help us in this, the knowledge base, which is the ground truth consisting of fuzzy if then rules, each of these rules is translated into a fuzzy relation. So the first rule, a1 implies b1, is captured in the form of r1, fuzzy relation. Similarly, the other rules, r1, r2, so on till rn. In the case of first aggregate then infer, what we would do is combine all of these relations, aggregate all these relations into a single relation r, and use this to obtain the corresponding b dash. So we compose a dash with r with any of the compositions, either the sub-t composition or the infi composition, to obtain our b dash. So if you use the sub-t composition, we call it the compositional rule of inference as proposed by Zade. If you use the infi composition, the Bandler cohort subproduct composition, we call it the BKS inference. So this is pictorially how we do FATI, first aggregate then infer, in fuzzy relational inference. There is also an alternate inference strategy, first infer then aggregate. In this case, given an a dash, to obtain a b dash, what we do is we take all these relations, we do not aggregate them beforehand. Instead, we infer b1 dash from r1 and a dash. Similarly, given this a dash, we obtain a b dash through r2, and so on and so forth till we obtain b1 dash from a dash and rn. Now these locally inferred outputs, b1 dash, b2 dash, so on till bn dash, all these ba dashes, we aggregate them. So first we infer all these ba dashes, then we aggregate them into a b dash. This is how we obtain the overall output fuzzy set b dash. Now if you look at similarity based reasoning, once again we are given an a dash, we would like a b dash, but now we are keeping these rules as such. So a1 implies b1, a2 implies b2, a3 implies b3, so on till a1 implies b1. Unlike in the case of fuzzy relational inference, we do not change them into fuzzy relations. Instead, we keep the rules as such. Given an a dash, we match this a dash to each of the antecedents and find the corresponding similarity values. So a dash is matched with a1 with a matching function. The corresponding similarity value is s1. The similarity of a dash and a2 is given by s2. Similarity between a dash and a3 is given by s3, so on and so forth till sn. Now, using these similarity values, we modify the consequence of the corresponding rules. So s1 modifies b1 to give us b1 dash, s2 modifies b2 to give b2 dash, s3 modifies b3 to give b3 dash, and s1 modifies bn to give us bn dash. Towards this end, we use a modification function g. Now, the final step, we aggregate all these modified consequence, much like in the way that we do in theta and obtain the overall output fuzzy set B dash. Perhaps you may have seen some relations or relationship between or resemblances between theta, first infer then aggregate, and SBR scheme. In fact, later on in one of the lectures, we will see how a fuzzy relational inference when the operators are specified in a certain way can also be looked at as a similarity based reasoning scheme. Well, a quick recap of the lectures that we have seen throughout this week. We are now very aware that a fuzzy inference system approximates a given system function by covering it through overlapping rule patches. This is the concept that we have put to good use when we try to build fuzzy inference systems. We have specifically discussed similarity-based reasoning schemes in this week. Two of the major types are that of Mamdani and Takagi-Sugeno-Kang fuzzy inference systems. We have also seen how to build fuzzy inference systems, both the Mamdani and the TSK type, using the fuzzy logic toolbox available in Matlab to approximate a given specified function, or even in a practical application where we only had some qualitative features of the system function. Finally, we have also seen the different components of the fuzzy inference system and how to source them in a practical application. In the next few lectures, we will discuss interpolativity of fuzzy inference systems. A good resource for the lectures that we have had through this week, the topics covered in them, is the book by Pacino and Yurkovich, also the book of C.T. Lin and George Lee, and the book by Professor Piaget. At this juncture, I would also like to point out some seminal works that we have discussed throughout these lectures. It is this paper in which Professor Zade proposed the compositional rule of inference way back in 1973. In 1985, Pedrich used the Bandler cohort subproduct composition to propose the BKS inference scheme in this work. It is in this work, published in the Journal of Man and Machine Studies in 1975, Mamdani and Asilian, they proposed their Mamdani fuzzy inference system in the year 1975. And Takagi and Sugeno, they proposed the TSK Fuzzy Inference System in 1985 through this article published in the IEEE Transactions on Systems, Man and Cybernetics. Some related works. It was mentioned during a few lectures that a Mamdani or a TSK Fuzzy Inference System is capable of approximating any continuous function to arbitrary accuracy. We have seen this with a few practical examples using the fuzzy logic toolbox in Matlab, but theoretically also these results are available. So this is one paper that deals with Mamdani fuzzy systems, showing their capability, the universal approximation capability of Mamdani fuzzy systems. There's another paper way back in 1998 which discussed how even with linear rule consequent, generalized Takagi-Sugeno fuzzy systems are universal approximators. Please recall, we have also used the consequent functions to be constant functions in the example that we have seen, the case of contrast enhancement using TSK Fuzzy System, and we have seen that it has more or less captured what we had in mind. This yet another paper discussing the uniform approximation or universal approximation capabilities of fuzzy relational inferences. And finally, as was mentioned, under some conditions on the operators, an FRA can also be seen as an SBR. This is something that we'll take up in one of the oncoming lectures, but this is one paper, a work related to that. So in the next few lectures and from henceforth, we will look at some of the properties that a fuzzy inference system should possess or we expect it to possess, the desirable properties that of interpolativity, continuity, monotonicity, and so on. In that quest, we will begin by looking at the interpolativity of fuzzy inference mechanisms. Glad that you could join us today for this lecture and hoping to see you in the next lecture. Thank you again.